Hi, Divyank, are you able to see me? Okay, very good. So, welcome to this first live session. Very good. So, welcome to this first live session. As you all know, I'm Baskar, and today I'm with one of our TAs, Nitin. So we have one more TA, Shubham. He is out of station now, so he did not join today. He will come probably next week, next time. Uh, so happy to see you. Let's wait for a little time if somebody else can join. Uh, Devendra, how to see how many people are there? You know?
Sir, I think in chat box,
Only in chat box we can see.
and here it is written 11 watching now.
Oh, I see.
So
11
11
people are
students
watching
are
because, okay, there are 11 people. That's good to start. Uh, I think we are now into fourth week, right? We are into fourth week. Uh, so we should like start talk continuously that, okay. Okay, so yeah. Uh, okay, thank you, Kajal. Thank you, everybody, for joining us. So I hope you are enjoying this course. I have also seen some comments about the course. It's only that the tutorials are little difficult. That's what you said. But we will try to balance this. So we are into fourth week, and what we have learned so far. Let us try to summarize. Uh, in the first week, it was little hectic because we had six uh, videos in first week, but the first video was a general introduction and so on. Okay, so there's no concept covered in the first week's first video. Therefore, in the first week also we had five uh, half an hour lectures. During this time, we have covered some mathematical preliminaries. Basically, we have covered Taylor's approximation, and then we have also covered order of convergence concept. Okay, so I hope Nitin also has discussed this,
Yes.
right? Okay, so you people are not joining in Nitin's thing. See, Nitin is a very nice teacher. Huh?
Thank you, sir.
And he teaches very well, and you should utilize his live sessions and uh, make your concepts more clear. Otherwise, what happens is, if you don't clear your concepts, you may not be very comfortable in solving the problems, right? So in the first week, we had very two important concepts. One is Taylor expansion. You may not see the actual usage of Taylor expansions till now, But once you go out of the linear algebra concepts and you get into the calculus concepts, which will come, I think, from the 6th week onwards, you will see that Taylor expansion is used quite often. In fact, in almost all the lectures, all the concepts, you will be using Taylor expansions. Okay. Of course, you all know Taylor polynomials, Taylor expansion and all, but from the numerical analysis point of view, it's also important for you to understand certain things, especially from the way the reminder term is actually dealt in the numerical analysis. Especially, you have to understand and write the Taylor expansions, Taylor polynomials, plus the remainder term correctly. Okay. What is the order of convergence of that remainder term is very important from the numerical analysis point of view. Okay. So this example, I think we have given with the cos and sine. So this is one thing that you have to note down, very important. And then order of convergence is also very important concept. Okay. Okay. Madam is also here. Okay, good. So yeah, please feel free to ask questions because this is one time that we all can meet and talk together, right? So this is very important. Okay. If you have any doubts, you can also send message to us. We will try to answer as and when we get the message as soon as possible. But this asking in live session is also very good. Okay. And then the order of convergence, we have two ways of measuring the speed at which the sequence converges. Okay, one is using the notation called big O and small o, and another way of measuring the order of, that is the speed of convergence of a sequence, is through concept called order of convergence. Okay, so we have covered these concepts in the, I think, third lecture of the first week. And you see, this is very important because in numerical analysis, we develop methods, of course, and then we want to see how well we are capturing the exact solution of our model, right? So in most of the numerical methods, we will be devising some way to generate a sequence of numbers or vectors, whatever it is, that we expect to converge to the exact solution. Okay? And we want to put these methods on a computer, right? When you go to put these methods on a computer, we also worry about how fast we can compute this solution. Okay? Because it is seen as a computational cost also. So, I mean, if you are solving a 3x3 system, for instance, it hardly matters. But in practical applications, you will be solving a problem, say, for instance, a linear system which is few millions or billions. Okay. Like, for instance, every search that you do on Google, it seems, I'm not an expert in this, but it seems I was told that Google is solving, I mean, not a linear system, but it is finding the dominant eigenvalue of a matrix which is called Google matrix, and its dimension will be around a few billions. Okay. So it cannot afford to take even minutes to find eigenvalue, dominant eigenvalue of that matrix, huge matrix, right? So even if it spends 1 minute, you know, you who is a searcher using the search engine may get bored to sit and wait for 1 minute to get any search, right? So in many applications, you want to have your solution in few seconds to few minutes to some, in certain applications, maybe few hours is okay. Okay, but what is important is you want to get the solution as quick as possible. Okay, for that reason, in real life, we also want to have the method that converges quite fast. Okay.
One doubt.
Okay. So therefore, the order of convergence which measures, yeah, Vidushi, I will just complete this discussion and then come. Okay, so the order of convergence is very, very important. It is a very important concept because when you develop any method, the first question people will ask is how fast your method will lead to a solution. Okay, this is very important. Okay, so then you need the tool to measure the speed of convergence of your method. That will directly tell you how fast your method will lead to a solution. And then the next is how accurate your solution at the end of the time, right? So these two are very important. The order of convergence tool is something to do with how fast your solution, your sequence will converge to the solution. Okay. Therefore, order of convergence is very important from the numerical analysis point of view. And this is what we covered in the third lecture of the first week. Okay, let's take these questions. Vidushi madam. Yeah, so please.
So the doubt is, sir, I have a doubt in big O and small o.
Hmm?
Is the convergence of sequence has any role in concept of big and small o?
See this big O and small o, they are actually tools to measure the speed of convergence of a sequence. Okay. See, just imagine that you have you have a vehicle, okay, and somebody asks you how fast your vehicle can go, okay. Uh, what you will tell you, okay, you may tell many things, goes very fast, this, that, but simply if you say my vehicle can go as fast as a BMW car, say for instance, if you say, that may be something which is, generally we have a feeling that BMW car is very fast and so on, right? So something like that. There are many other very fast moving cars. I'm just telling one few example, just an example. So like that, in sequence, if you have a method, it generates some sequence, you don't even know how that sequence looks like, right? So you put that method in a computer and that computer will compute. You don't know how the sequence even looks like. Okay? So if somebody asks you, how fast your sequence will converge, it's better to compare your sequence with somebody else and say that yes, my sequence will converge as fast as this guy. Okay, like for instance, you have the sequence 1 by 2 to the power of n. Okay, when n tends to infinity, you roughly know how fast 1 by 2 to the power of n will converge, right? You can just, even if you want to have a very concrete feeling, you can take 1 by 2, 1 by 2 square, 1 by 2 cube like that and see. You can even plot that and see how fast it decays to 0, right? So you can easily understand 1 by 2 to the power of n, how fast it goes to 0. Now, if you tell that, okay, my methods which generates the sequence, that goes to 0 as fast as 1 by 2 to the power of n goes to 0, that may give a kind of, okay, oh, very good, that's pretty good, like that, okay. So big O and small o in that way, these are tools to compare your sequence with some well-known sequence, okay. So that is what the purpose of big O and small o. Therefore, these definitions have the purpose of these definitions, okay, whether see the role in the concept of big O and small o. These big O, small o concepts are tools to measure the speed at which a sequence converges to its limit, okay, by comparing these sequences with some well-known sequence. Okay, so that is what the thing is. So the second
Yes, sir, I'm reading.
yeah.
So this is the doubt by Raja Priya.
Okay.
We solve assignment questions, but how could we check that is correct or not before uploading? Because we upload the MSQ questions,
Yeah.
answer itself we answer. I mean, we get no mark how we prepare, sir.
Okay, see, of course, it's an exam. Okay, so in the exam, if I sit and write the answer and see if my answer is correct, then only I will give my paper to my teacher in the class. Then, see, that's not exam, right? So what we do is, of course, we are giving the answers at the end of the week. Once the assignment time is over, we are giving the answers. So you can compare your, see what you are doing is when, roughly I will tell you how I am giving questions. Okay. Probably I can share and write. Okay. Hmm?
Share, you can share from there.
From here?
So if they told me, so this click on share.
Share and then yes, this is, share. Okay. Okay, I can just go to any of this. Maybe I will open order of convergence itself. I will open. Okay, so this is order of convergence slide, but my aim is not to show the slide, but to write and show you. You see, every week has 5 lectures, 5 lecture videos, right? So roughly speaking, each video has 3 questions or 3 more questions. Okay. So each video will roughly have 3 questions of each 1 mark. Each 1 mark, or at least we make sure that 3 marks are little plus or minus weightage on each video. So what you do is you watch one video, understand it. We also give notes which is covered in the lectures, right? So you read the notes, you see the video. Once you do that, you come to the assignment, see what are all the questions which are, you can, once you understand the video, you can see what are all the questions which are covered in this lecture. Try to solve them and write the solution and keep, okay? Like that, once the week is over, you are submitting, and then once we release the answers, you can compare that with your answer and see where you made mistake or where you performed well. Okay, this will help you also to uh, prepare for the exam, right? See, your assignments are basically to prepare yourself for the exam. Okay, that's more important for you. Exam preparation is more important for you. Of course, if you ask me, I want to know as soon as I solve the problem whether I have solved or not. That is not the purpose of this of our assignments, right? So if I stop like this, it will stop sharing, I guess, right? Okay, so I think we came back. Yeah, so the next question.
So the next question is by Divyang Tiwari.
Hi.
Is it essential to build a strong foundation in real analysis to handle the proof-based aspects of numerical analysis? Being from a CS background, I don't have much exposure to proof-based mathematics.
I see. Okay. See, in our course, okay. See, there are two ways that I can answer. Suppose you want to train yourself as a numerical analyst and want to do research on some research problems that needs a strong numerical analysis, then real analysis is very, very important. Okay. It's always better if you get a good knowledge on real analysis and then come and do this course. It is much more enjoyable for you. Okay. That is why in our course, what we do is we cover a lot of very rigorous stuffs which are needed for numerical analysis from the creator's point of view. Okay. But from the in the questions, we don't ask so very rigorous questions. Okay, we will try to keep the assignment questions as well as exam questions a little light. It's not that we will ask easy questions or trivial questions, but if a student has gone through a good calculus course, then it should be okay. For instance, if you have understood the lecture 1 and 2 very well, Taylor expansion and order of convergence, this is all the tools that we will be using, which are also covered in calculus. But if you have done real analysis, your maturity in these topics will be much more. That's what is important. Okay. So apart from that, we don't get into very deeper analysis side. So therefore, it all depends on what is your interest. If you want to develop the skill of being a numerical analyst, it's better you go for first real analysis and then you do this course once again, maybe. Okay, but just to do this course and get a good knowledge on what we are doing in this, then a good calculus up to the level of that first 2 lectures, that's good enough.
So next is a comment by Shubhamay Ghosh. Sir, the notes you are providing, they are very helpful because they also have some extra assignment questions.
Yes.
Thank you for that. But will you be able to get the solutions to these questions as well?
See, solutions to these questions, we have probably we have a solution to these questions, but they are not properly organized. Okay, so what we will do is at the end of this course, we will try to post these things because during the course we may not have time to sit and organize all these solutions, because whenever we frame the question, first we will solve it and keep. Okay, so all this what we do is we just roughly file it and keep. Okay, so we never even checked once whether we have written it well. Of course, we check whether the solution is correct or not, but we don't see. It's not just writing the solution. You have to also put it in a nice form that a student can understand, right? So that exercise perhaps we have not done. During the course, we may not have time. Maybe after the course ends, then we will probably share this to some interested students. Yeah.
Next is in the continuation of the last comment. The fellow says, so that we can check our solutions whether they are right.
Yeah, that is true, right? See, certainly we are giving solutions for the assignment problems. Okay, and so we that will give you certain maturity with which you can also try to see. If you have any difficulty in some questions, then you can always mail us, or you can ask in the live session, we can discuss. If you mail also, we can discuss the solution of those problems. More importantly, Nitin is spending time, in fact, 2.5 hours time he is spending, okay? So I have given him all my rough work of solutions. You got the solutions, yes, right? So he has, of course, you can also come to the his live session, sit with him and discuss. See, whatever we give, the questions in the book notes, you can ask the doubts in the live session and get it solved. Okay, that's a good idea actually. Okay, so you please come and discuss with him. Yeah,
I want to add one thing. Like, because you also are instructed me to discuss those basic real analysis and linear algebra techniques. So that fellow asked, so that could be helpful. Like,
yeah, Divyang, right? Divyang asked.
Divyang Tiwari.
Yeah, so Divyang, you can also ask all your real analysis doubts to him. because I think you will be sitting for 2.5 hours on Sundays,
Yes.
right? So that's a big time. You see here, now we will be just sitting for 1 hour, right? We are just chit-chatting. I mean, I don't think we are doing anything serious, right? So we are just chit-chatting and then 1 hour goes. Okay, but Nitin is, he will sit and he will explain you real analysis. He's expert in analysis. I can say that any analysis is an expert. Real analysis is like for him, it's just easy. Okay, so therefore you can ask any doubt in real analysis. Also, if you want to ask, you solve some problems which we gave in the lecture notes, and you have any doubt, you can ask him. He will solve and show you how to do that. Okay. So since we have not put it in a proper format, we cannot, publicly share it. That is the problem. Okay. But it's not that we don't want to share. We cannot publicly share because we ourselves have not standardized it. Okay. But he has all the solutions. So if you ask any question, how to solve and what is the idea, he will explain all that. Okay.
So next is a comment again by Divyang Tiwari. Okay, thanks, Professor. I was primarily asking from a perspective of a research. Would also refer to Stephen Abbott's understanding analysis after this course to get a stronger real analysis base.
Yeah, that's good. From the research point of view, it's better to have a strong, even if you have strong thing and then you come back and watch these videos, you can understand many subtle things which are there in certain methods, especially in the forthcoming chapters on nonlinear equations and so on. Okay, so you will certainly enjoy it. Yeah.
Next is a thanks note by Shubham Ghosh.
Okay.
Thanks a lot, sir. I will attend Nitin's live classes.
Okay, that's good. Okay. You see, he is spending a lot of time. No, none of you are coming.
Other is question by Divyang Tiwari. Thanks. Might have missed the mail for office hours session. Are they conducted every Sunday?
That's correct, right? It's conducted on every Sunday.
Every Sunday, 3 to 5 p.m.
Yeah. So maybe Bharti madam can send one more mail to everybody. Just one mail is very likely that people will miss it, right? So. Okay, so let me continue my general summary of of what we did. So after the second lecture, that is the third lecture in first week, we had 2 more lectures in first week. Okay, so that was on the error that computers commit. Okay, so generally it's not that when you devise a numerical method for some mathematical model, we commit error mathematically. Even when you go to implement these methods on a computer, even computer commits certain error. This error is precisely when the computer stores the numbers in its memory. It cannot store a number in its full form. For instance, 1/3 is a number which has 0.3333 and it goes on infinitely, right? So computer cannot hold a number with infinite mantissa. So it has to truncate somewhere. Generally, it rounds off the number and holds the only finitely many digits in the mantissa. That is its limitation. Because of that, well, if you see, it commits very small error because in double precision, generally it takes 52 bit in the mantissa, right? Therefore, it's of course committing very small error, but sometimes it makes absurd mistakes. Okay. In fact, in the second week, first lecture, we introduced, not first lecture, I think the second lecture of second week, we had a Python session. In the first Python session, I have shown you some absurds that computer makes. Okay, you can even show these programs to some 5th standard, 6th standard kids or more. They will enjoy that. Okay, so computer makes such a trivial errors. Okay, and in fact, from this trivial error to some very serious errors, the computers can make, and that has to be carefully taken care of when you are doing computations. Okay, so this is what I was trying to impress you on the this Python session, first Python session, which was the second lecture in the second week. But before looking into this lecture, you have to go through the first week last two lectures. Okay, here we are showing how a computer can make these rounding errors and what are all the disasters that it can, it made many disasters in real life. Okay. The main problem is the losing significant digits. So in these lectures, we have defined what is significant digits and how the loss of significant digits can happen in the basic arithmetic operations, and how this, once you make error in one computation, how it propagates into the subsequent calculations. This also we have explained. Okay, so these are the problems of these are the discussions we made in the second half of the first week. Yeah. So, and then we have also introduced a tool called stable computation and unstable computation. Suppose you are evaluating a function on a computer, how will you know that evaluating this function is going to be good on a computer in terms of error that it can accumulate while computing? Okay, so when you make a rounding error, every stage of a computation of a function will involve some error, right? So it will be nice if I show you some. Propagation. Okay. So this is where I guess I was. Yeah. So if you see here, this is what I'm saying. So you want to evaluate a function f on a computer. Now, mostly you want to evaluate it at a point x, but your computer may be taking that value as some approximate value. Therefore, your intention is to find the function value f of x, but your computer may be finding the value using xa, which is approximate value. In that itself, it will make some error. Every step of the computation, the computer will make error, right? Therefore, it's very important for you to understand, if I have a function, I'm dealing with the function, I'm going to compute the value of this function on a computer, whether my computer is going to give something very close to the exact solution or something drastically different from what is exactly it is supposed to give, right? So that is that depends on what is the condition number of your function. Okay, so this concept is very, very important. Condition number of a function. Later, we also introduce condition number of a matrix. Okay, so I think you would have gone through this also in third week. Condition number of a matrix. So this condition number will tell you how dangerous or how peaceful it is when you go to evaluate a function value or a matrix, any matrix computation in terms of the linear system. Okay, so this is what we did in the first week. Basically, we just gathered some tools as a mathematical preliminaries to understand this course, and then we also understood how we have to be careful with the computer when you go to implement your methods on a computer. What kind of errors the computer will make and how dangerous it can be when you do the computation by ignoring these errors. Okay. And then, well, how to completely stop making errors on computer. Well, that is not possible as per today's technology. You have to live with the errors that your computer gives. Okay, the only best thing that you can make is that you understand it and be careful when you are doing the computations. Okay, that's all you can do. Therefore, in these lectures, that is the last two lectures of first week, explains you what are the ways that a computer can make errors and how you can safeguard them as far as possible. It's not completely, you cannot come out of that, but if you are careful, you can safeguard yourself. At least you be aware of that. Okay, I'm going to do this computation on a computer, and this problem is so bad. I'm going to evaluate certain functions which has a very big condition number, and that is going to be very dangerous in general when I go to compute it on a computer. See, this kind of information can be learned by going through this lectures. Okay. And then when you come to the second week, the first lecture is something I spent some time on solving some problems. Since we have packed a lot in the first week, I went very fast in the last two lectures, especially where I wanted to explain certain things, but I could not have time to do that. So in the first lecture of the second week, I did these things, especially from the mission epsilon point of view. There are some concepts. Um, I think Vidushi also asked some questions. I answered in the email, not here, I guess. Okay, I hope Vidushi has understood. If you have not understood, you can ask that question now. Okay, I saw your email only today. Vidushi, your discussion is not appearing on the discussion forum. I luckily saw your email today, so I just replied to that. If you still have doubt on the mission epsilon, you can ask me. Otherwise, in the second lecture of second week, we have introduced Python coding. Okay? But it's a very elementary introduction to Python. It's no way we can justify it because Python is a vast, and just in half an hour, of course, we can't do it. But I have just told something which are essential for our course only. Okay, so that's all we did in the second part, and rest of the things as and when we do, we will cover that. Okay. Yeah.
Vidushi commented,
Yeah.
Sir, I got it. Thank you for the
Okay,
concern.
so that's good. And then once we have done all this, in the third lecture of second week onwards, we started a new chapter that is on linear systems. In linear systems, our interest is to develop two classes of methods. One is direct method. Direct methods give exact solution if there is no rounding error involved in it. Okay. So, for example, Gaussian elimination method, which you all must be knowing very well, is a exact is a direct method because if there is no rounding error involved in it, it perfectly gives you exact solution. Okay. There is no, otherwise mathematically there is no error involved in it. You simply do some elementary row operations, bring the given coefficient matrix to upper triangular matrix, and then do a back substitution. That's all. It's a very simple idea. But when you go to implement it on computer, that's where you will get a solution which may not be anyway close to the exact solution. So we have given an example like that. Okay, and in fact, there is one interesting example in the assignment also. Uh, to do that assignment, I expect you to first develop a Gaussian elimination code for just 2 by 2 matrix and then apply it to that problem and see. So that you will enjoy that. It's a very nice example. Okay, so I think its solution is supposed to be 0, 0 or 0, 1 or something, but it gives a very big solution. Okay. So that also tells you how stupid a computer is in general. Okay, so you have to be very careful. You cannot blame your computer for that. Okay, computer will simply do what you want. Okay, so in that process, it can make disasters. Okay? So that is why in numerical analysis, especially if you want to train yourself as a numerical analyst, you have to understand the analysis behind all these methods. Okay, so that when you go to develop new methods as a researcher, you should know different tools that people have used to analyze these methods. Okay, this is mainly to make yourself more careful when you especially go to do things on the computer. Okay, what generally we do is we will very conveniently say that I don't want to do any computation on a computer, right? So we will only do mathematics. But as an engineer, often, so people cannot afford to do that. They have to implement their methods on computers. Okay, therefore, for engineers, it's more important to understand all this analysis than for a mathematics. Okay, we just do some mathematics and we are happy with that. Okay. We don't care when you go to put it on a computer whether the computer will give the answer that we really want or it just gives you something. Okay, we don't care for that. Okay, therefore, for engineers especially, it's very important to understand all this analysis. Okay, so we also introduced the LU decomposition. Okay, these are some interesting methods. We have also introduced Cholesky's factorization in that week. So that completed our second week. The second part of the second week is mostly introducing these direct methods. Okay, so they are very easy. Therefore, when it comes to the third week, of course, initially I have introduced a way to see how fast a method can be on a computer. Okay, so that is the efficiency test of a method. Okay, this can be done for any method. But it's mostly a subject in algorithms and so on. Okay, so it's not very much directly linked to numerical analysis. Numerical analysis is mainly to develop methods and do some error analysis on the method. However, as a numerical analyst, you should also know how to do efficiency test of your method. Okay. So for that, to illustrate, we have taken Cholesky's factorization and Gaussian elimination method and did the efficiency. We measured their time efficiency. Efficiency means that how much time it takes on a computer to arrive at the solution. Okay. Of course, you cannot precisely do, or one way to precisely do is to just run the code and measure the time. You have your computer, you can measure how much time it takes to finish the computation. But generally, that is not what people prefer. They try to understand the time efficiency of a method by counting the number of arithmetic operations involved in a method. Okay. Obviously, the more arithmetic operation involved, the more time your computer will take, right? So that's very clear. For that reason, people do this exercise. Once they do a method, they will try to, the immediate thing is what is the efficiency. Then they will count the number of operations. And in counting the number of operations also, it's not very important that you have to tell, okay, these many operations are there. Like very concrete numbers you need not give. You just have to tell them, suppose you are working with a linear system, which is an n cross n system. Then what is the order of the number of operations in terms of n? Okay. So in that way, we have shown that Gaussian elimination method and Cholesky's factorization, the number of arithmetic operations involved in this method is of big O of n cube. It means if you are working with 1000 cross 1000 system, it is going to take the number of operation involved is roughly something like 1000 cube plus more. Okay, there is something more is there, but what is important is the leading term. It grows. So if you increase the system's dimension n to n plus 1, it increases from n cube to n plus 1 cube. You see how much jump it will have by if you just increase one dimension in your system, how much the number of operations involved. Okay, so these are the interest for numerical analysis to see how your arithmetic operations order wise they will see. Okay, they won't see exactly what is the number and all, they don't care, but they generally care about the order in which it increases if you increase the parameters. Okay, in a linear system, you may think n as a parameter, the dimension of the linear system. Similarly, in some other problem, if you are working and it involves certain parameters, what generally people do is they identify what are all the important parameters, big parameters involved in the model, and then they will correspondingly count the number of operations in the method and see how the operations increase as you increase the parameter number. Okay, so to illustrate this, we did this exercise with Gaussian elimination method and Chomsky's factorization. Okay, so that ends our direct methods, right? And then we went into we want to go to iterative methods because our interest is to introduce two class of methods. One is direct methods, which we finished by second week and a little bit of third week. And then our next interest is to go for iterative methods. But before going into iterative methods, we want to learn a tool called matrix norms. Okay? Because this tool is very important for us to do the error analysis in the iterative methods. Okay? So in iterative methods, we will be generating a sequence called iterative sequence. Okay? An important point is whether our sequence is going to converge or not, right? Otherwise, you will be putting that method on a computer. Just imagine that your method is going to generate a diverging sequence. Then lifelong, your computer will keep on computing without arriving at any conclusion, right? So therefore, before giving any problem to the computer, you first make sense that the problem has a solution first and foremost, okay? So that's very important. Once you make sure that it has a solution, then you have to also check whether your method is going to give you solution in certain finite steps. Otherwise, if it is going to go on doing certain things, then your computer may not finish the job, right? It has to take only finite step. It may not give exact solution, but within finite step, it should give a solution which is acceptable for you in terms of accuracy. Okay. So to measure all this, you should also have a tool which will tell you how to do the convergence analysis. Okay. So that is what we are trying to understand in third week. It is matrix norms. In fact, condition number of a matrix is defined in terms of matrix norm, which is a very important norm called subordinate matrix norm. Okay. So that is what we are doing in the third week. We are mainly interested in introducing subordinate matrix norms, and then we are telling what is how to define a condition number of a matrix. Okay. Finally, we have made everything in the form of formulas. Okay. So basically, we use three types of norms. One is L2 norm, which is physically realistic, and then the next one is L1 norm and L infinity norm. Very standard question that students ask is, when I have a physically realistic distance concept, why should I worry about learning a general concept of distance called norms? And then why should I even measure all my errors in terms of some physically unrealistic norms, right? So unrealistic norms. The problem is if you are working with the physically realistic L2 norm, which is the Euclidean norm, its corresponding matrix norm is something involves the spectral, which is a spectral norm. Okay, you have to compute the eigenvalue of that. Okay? Eigenvalue, as you know, is very, very costly computationally. Often it may take a lot of time. Okay, just to do analysis, and doing analysis is for your own satisfaction. You cannot afford to spend a lot of time in doing analysis, right? So what people do is, because of that, they develop some toys which mimics the behavior of the physically realistic stars. That is L infinity and L1 norms. And their subordinate norms are very, very elementary, easy to compute. Okay. Therefore, what they do is they do all their analysis with this simply computable norms. Okay. Yeah, just there is an announcement.
We have an announcement by Bharti ma'am. We post announcement that reaches your mailbox. Please keep checking your inbox daily. We will plan another session as per Professor Bhaskar's convenience and post the announcement to you all.
Yeah. So you keep checking your mailbox of this. I hope the mailbox means the mailbox which is provided by in the NPTEL. Right?
Yes.
Okay. So that is why we need this toys. Okay, so L1 norm and L infinity norm are like toys. They are not going to give you physically realistic measure of distance, but that they are enough to understand the at least the convergence error analysis in the linear systems. Okay, and computationally, more important is computationally they are more simple to compute. That's why we go for such norms. And that is the purpose why we spent lot of time in understanding what is the definition of norm, what is subordinate norm, and so on. And then we go to define the condition number of a matrix. And we have also seen how condition number can be used to measure the relative error involved in the approximate solution when compared to the exact solution. Okay, so that also we have understood. That itself will tell you how important the condition numbers are. And then once you gather all these tools, then you are ready to face the iterative methods. Okay, I think that is coming in the 4th week. Iterative methods. I think that is running right now. Maybe you started it only yesterday. Therefore, there's no point in summarizing it. Maybe in the next live session, I'll summarize from the iterative methods. I hope you are enjoying this course. You have any further questions, you can ask me. Or if you have any difficulties, like, if one comment I got is that the tutorial problems are very difficult. Okay, so maybe we'll try to balance that. If you have any other difficulties, you can tell us. Okay, Nitin is always there. He is spending 2.5 hours. I'm telling you. Okay, so you should utilize that.
So we have a question.
Yeah.
By Shubhamay Ghosh.
Yeah.
Sir, in the subjective assignment, are we supposed to print the L, U, M, etc. matrices as shown in the lecture, or only the solution if the system will suffice?
See, what you do is you simply print the solution alone. Okay, so what you do is you just take the program that I have shown in the lecture, the Gaussian elimination code. You just modify it to run only 2 by 2 matrix. Okay, don't give us a very general program. Just modify that to give a 2 by 2 system solution. Finally, you only print the solution. Okay, so the solution x equal to what is the first component, what is the second component. Okay, so our TA will just to open it. He will have his own 2 by 2 matrix, his own B right hand side. He will just plug in that. He will see whether the solution is as per what it is supposed to give, and he will just give you 3 marks. Okay, so it's not very difficult. Just take our code, which is shown in the lecture. First, understand it. I'm not giving you code because once I give you code, you may just try to, some student may just try to blindly work on it. Okay, so we don't want it. That's why we want you to type it. At least when you are typing, we'll go through the lecture once and type it. In that way, you may understand the functionality of it. If you give the code, it may just be like, in certain things we may give code because that is little tricky. So we may give code and ask you to just change certain lines. Okay, but in this case, it's not very tricky. It's very easy. So you just go through the video. Just make the same program is made for 3 by 3 matrix. You just make it for 2 by 2. print the solution and give us. That's all. Okay. Yeah. Yeah. So you have to check your registered ID and also in NPTEL, and you keep watching what is the activities going on. Okay. So you may not get any mail in your personal mail like Gmail or whatever it is. It is the mail which is provided by NPTEL. Okay. So any other question? How many?
19.
Okay, 19 is not bad. Okay,
Not
okay. But you see, we have around 60 registered. I mean, 60 people are submitting. So registered or enrolled maybe more, but very happy to see that around 60 plus people are submitting the assignments. Don't lose the confidence. Okay, so just keep on submitting. Don't worry whether it is correct or not. But once you get the solutions, you try to learn. Okay, because the final exam actually matters. And of course, after all this, our aim is to train ourselves as a numerical analyst, right? So that is what is more important. Okay. So it's good. I hope you all will come for all the live sessions and you will continue in our course. Okay. And we hope to see more people in the next live session. Thank you very much for your time. No, that's we finished.